Good evening, everyone. I am Madhvi Singh. It's my pleasure to introduce our esteemed guest, Dr. Akshay Sir, for today's session on linear algebra. Akshay Sir is an expert in the field, and I'm sure his insight will greatly benefit us. Let us give a warm welcome to Akshay Sir. Over to you, sir. You can continue. Thank you, sir.
Thank you, ma'am. Actually, the second device is not, you have to make me host.
Okay, sir. Can you? Okay, let me check. Done, sir.
Okay. Okay, thank you for the introduction once again. So, and last time we stopped at the discussion. So, suppose C naught denotes the space of all sequences, real sequences, which converts to zero. And that day I said, it is very easy to prove that this forms a subspace, right? Now, that day, let me recall. Suppose V is a vector space, W is a subspace of V. If V equals to W direct sum, say W2, then the dimension of W2 is called the codimension of W in V. Now the question is, if your space V is C, which is the collection of all real sequences, which are convergent. They may converge to any point, but they all are convergent. Now the subspace W is C naught, the collection of all real sequences which converge to 0. Now the question is, what is the codimension of C naught in C? So can anyone tell me the answer? So what is the codimension of C naught in C? Okay. So suppose Xn is any sequence in C. So this will converge to some point, say X, right? Now this point is fixed. This X is fixed, right? Now if X is 0, then what can you say? Xn belongs to C naught, right? Now if Xn, if this X is not equals to 0, this X is not equals to 0, so what can you do here is, so where X minus X will converge? This will converge to 0, right? So this sequence Xn minus X will belongs to this C naught, right? Now if you take this sequence, say Zn, such that each entry is 1 for all n, right? Now if you multiply this sequence by X, so what will be the sequence? The constant sequence 1, the constant sequence X, right? Now if you add both these sequence Xn minus X plus that X into the sequence Zn, so this will be equals to your sequence Xn, right? Because this Zn is your constant sequence 1, constant 1 sequence. Now you can also check that this Zn does not belongs to C naught, because it is the constant 1 sequence, and this Zn sequence also belongs to C because it is convergent, converges to 1. So this is, what can you say? This is, the C is equals to C naught direct sum span of this Zn sequence, and this is constant one sequence, right? Now what is the codimension of C naught? What is the dimension of this space? This is only one member, right? The span of this, so dimension of this is 1. So from here, what can you say about the codimension of C naught? What is the codimension of C naught?
1.
Is equals to 1, right? Although it's a very big space, C naught is a big space, C is also a big space, but the codimension of C naught is only 1 in C. Okay. So now let me start with the linear transformations. So what are linear transformations? Suppose you have two vector space V and W, right? And both are on the same field. Field should be same, say F, right? So a function from V to W, this is a function from V to W is said to be linear transformation or linear function, not functional, function is said to be a linear transformation or a linear function if it satisfies the following properties. So for first property is t of x plus y is equals to t of x plus t of y. This should hold for all xy belongs to the domain space V. Right. The second property is t of alpha x is equals to alpha t of x for all alpha scalar and x vector p, right? So these two properties are actually equivalent to t of alpha x plus y is equals to alpha of tx plus t of y. Either you prove these two properties or you prove these properties, this property alpha scalar or xy vector. So both are equivalent. This one statement is actually equivalent to these two statements, combine two statements. Okay, and this one is also equivalent to, so t of summation
Hello.
alpha I. Yeah.
Sir, I'm getting problem in my microphone. That is why I could not connect you. And the problem, the very first beginning, you have discussed. I have a problem about that regarding question. Can I ask this in the last session?
In the last you can ask.
Okay, okay. Please continue, and I will ask again.
Okay, so this statement is actually equivalent to, so the t of alpha I I is equals to 1 to 10. You take 1 to n, any linear combination. So this should be equals to summation alpha I t of I is equals to 1 to n for all x1, x2, xn vectors, and alpha 1, alpha 2, alpha n belongs to the field. So either you prove these two property, these two statement, or you prove this statement, or you prove this statement. So all are actually equivalent. Okay. Now, so what properties should satisfy by this? I should give some examples. So first example is the simplest one. called zero transformation. So what is this transformation? Suppose T from V to W, and all the member of V maps to 0 of W. This is the 0 of W. So since here we have two 0, 0 of V and 0 of W. That's why I'm writing here 0 of W. Okay. So this is the linear transformation. This is called this is a linear transformation, and this transformation is called zero transformation. So all members are going to 0. Right. Second one is you can take T from R2 to R, and you can define as, so member of R2 will be of the form x comma y, or x1 comma x2, whatever you want you can write. So suppose x comma y, right? So suppose I'm writing T of x comma or R2 to R2, suppose I and defined as x comma 0. What we are doing, we are just making the second component 0, right? So this is also a linear transformation, and this transformation is called projection of R2 onto x-axis. You can check it, this is a linear transformation. And third example you can take, so I should take infinite dimensional vector space C01 to R, and suppose you can define, you are defining your transformation as T of f equals to just value of f at 0. This is also a linear transformation. This is actually called evaluation maps. Okay, so what properties a linear transformation have? So properties. So first property is T of 0 will always be equals to 0 W. So this is what this property says: 0 element will always maps to 0 element. It may happen that this 0 may is different from this 0, but if your transformation is linear, then 0 member will always maps to the 0 member. Second, what property a linear transformation have? Suppose A is subset of V is linearly dependent, then T of A will always be linearly dependent. It always maps linearly dependent set to linearly dependent. Now, what about the linearly independent? Suppose A subset of V is linearly independent. So what can you say about the T of A? So it may or may not be linearly independent. The easiest example is the zero transformation. Take this zero transformation. You take any linearly independent set in V, so it will not map to linearly independent subset of W. Or non-zero transformation also you can take. Just take this transformation x1. You take this transformation from R2 to R2, right? So you just take T of x comma y is equals to x comma 0, right? Now what can you say about 1 comma 0 and 1 comma 1? This is linearly independent. This is a non-zero linear transformation, right? So what is the image of this? 1 comma 0 will be 1 comma 0. What will be the image of 1 comma 1? It will be 1 comma 0.
1,0.
So this is linearly dependent, right? So the question is, when T maps linearly independent set to linearly independent set, right? So for this, you can write this result. So T maps linearly independent set to linearly independent if and only if T is 1 1. What is 1 1? So if T of x equals to T of y for any vector x and y, then x should be equals to y. This is 1 1 or injective. Okay, so this is if and only if. Even you can add some more statements to it. So this is valid for all infinite dimensional or finite dimensional, all the vector spaces. Okay, now the point is, suppose what is null space? Let's define null space and range space. So even you can add one more point here. So this is if and only if T of x equals to 0 implies x of 0. So suppose T is a linear transformation from V to W. So what is the null space of T? Denoted by capital N of T. So all the vectors of V such that T of x equals to 0. Or you can write it, yeah. So this is equals to T inverse of 0. Right. So from here, what can you say? So this is if and only if your null space is only 0. Right. And then you can check that this always form a subspace of V. Right. So if and the dimension of null space of T is called the nullity of T. So this is if and only if nullity of T is 0. So you can add many equivalent statement to it, and if okay, that we will add later. Okay, so sub range space we can define here. Range space of T is all the vectors y belongs to W such that y is equals to Tx for some x belongs to V. This is actually the range of T. So this is also can be written as T of V. Okay, so this is the range of T. So of course this is a subset of W, right? And you can verify that this is always form a subspace of W, and the dimension of range of T is called the rank of T. And a famous theorem says, is called rank nullity theorem. If dimension of V is finite, dimension of W is finite. Even this, you don't need this one, you need only this one. Then and T is any linear transformation from V to W, then rank of T plus nullity of T will always be equals to dimension of V, the domain space. This is called rank nullity theorem. Okay, and if this is definition, if a linear transformation from V to W is bisective, and isomorphism. And V and W, two vector space called isomorphic. This is the notation, isomorphic. If there exists a linear transformation, there exists an isomorphism between V and W. And you can prove that if V is isomorphic to W, then dimension of V is equals to dimension of W. Okay, even the for we are talking about the finite dimensional, and the converse is also true. Dimension is equal, dimension of V and dimension of W are equal, then V and W are isomorphic. Okay, and now what can you say about the infinite dimensional? So the question is, suppose T is a linear transformation from V to W, right? And dimension of V is infinite. And dimension of W is infinite. So before this, I can add some more statement here. Yeah, here you can add some more statements. So if this is if and only if your dimension of V is equals to dimension, okay, don't add this one. Okay, come here only. Okay, so suppose T is a linear transformation from V to W. So take your V as C naught naught. Eventually zero sequences, or you just take C, the sequence, all convergent sequences, and W is also equals to C. So this T, and just this is, suppose this is a sequence, and you map this sequence to 0, x1, x2, like this. So you can check here that this T is 1 1. So can you tell me, it is this T onto or not? Is this onto?
Sir, question, please repeat one question.
So, suppose your V is C, the space of all convergent sequences. W is also equals to C, and your linear transformation is defined as x1 x2 maps to 0 x1 x2, like this. Now I'm saying it is very easy to prove that it is 1 1. The question is it onto?
Yes, because of for infinite sequence, we can add or some finite number of element we can add or uh, subtract, eliminate, there are no harm to this original convergence of the sequence.
Okay, so let me ask you in the different
Okay.
way. So this is so onto means all sequence must belong to the range space, right? All convergent sequence
Yes.
must to
Yes.
belong to the range space of T. Now the question is this constant one sequence is a convergent sequence.
Yes,
Is
sir.
it belongs to the range space of T? If it is belongs to the range of T, then T of x will be equals to this. Suppose this element is Z. So T of x belong equals to Z for some
Yes.
x belongs to C.
Hmm.
The space of your you can write C or V, right? Now x will be a sequence, so it will be like xn, right? So what is T of xn?
Yes, sir. Yes.
What is T of xn? So xn will
So,
be like x1, x2, like this. So by the definition of this linear transformation, so this will be equals to 0, x1, x2, like this. So the first member is 0, but here the first member is 1. So Z will never belongs to the range space of T, right?
yes, sir.
So T is not onto or surjective, right? Even though both the spaces are same, T is 1 1, but T is not onto. But this will not happen in the finite dimensional. So suppose T is V to W and the dimension of V is equals to dimension of W and it is finite, then so this is a linear transformation. Then T is bijective. Bijective means 1 1 and 1 2 if and only if T is 1 1, if and only if T is onto, if and only if null space is 0, if and only if range space nullity is 0, if and only if range is, so bijective means onto means this is if and only if range space is the whole codomain W. This is if and only if rank is equals to the dimension of W. So all these are equivalent for finite dimensional. Once you have a linear transformation from V to W and the dimension of V and W are equal and finite, then you just need to check it is it 1 1. If it is 1 1, then it will be bijective. For that you just need to check what is the null space. If it is if the null space is 0, then it will be 1 1. So any one of these statement you can check, all the other statement will be equivalent to that. Okay. Okay. So suppose
Yes, sir.
let me ask you one question. Suppose T is a linear transformation from R3 to R3 defined as T of x, y, z equals to x plus y then 0 and Z. Now, can you tell me what is the null space of T? You can check that this is a linear transformation. Now, the question is, what is the null space of T?
Span of 1 minus 1 0.
So, null space of T will be X, Y, Z such that, so suppose you take any element X, Y, Z in R3 and you are saying this is equals to 0. If this member belongs to the null space, that means T of this member will be 0. Now, what is T of X, Y, Z? This is X plus Y 0, comma Z. So this is equals to 0. So what is the 0 element of R3? 0, comma 0, comma 0. Right? Now, so from here what you can say? Z equals to 0. So your Z should be equals to 0. Right? And your X must be equals to minus
minus
Y.
y.
So second condition is X equals to minus Y. Right? So what you can write here is X minus X, then 0. X belongs to R. Right? Now, what is the dimension of this space? What is the dimension of null space?
1.
1. Just you just need to take the value of X. Right? So this is actually span of 1 minus 1 0. Right? So the dimension is 1. Now, what is the rank of T? What is the
2.
rank of T? By rank nullity theorem, it will be equals to dimension of V minus nullity of T. What is the dimension of V? 3. Now, what is the nullity of T? 1. So the rank is 2.
2.
Right? Okay, let me take some other example. Suppose T is your M n cross n matrices to R. And how you define this transformation? T of A equals to trace of A. So is it a linear transformation? Okay, for that you just need to check what is trace of A plus B. And this will always equals to trace of A plus trace of B. Right? Now what is the trace of alpha times A? This is always equals to trace of alpha into trace of A. Right? These are the properties of a trace. So this is a linear transformation. Okay. Now can you tell me what is the null space of this? So A belongs to M n cross n matrices real such that trace of A is 0 by definition of T. Now if A is A11, A12 like this, A1n, A22, A2, A21, A22, A2n, this is A n n. Right. So what you can write here, A belongs to M n cross n matrices such that the summation of I equals to 1 to n, this summation should be 0. Right? Now from here what you can write? A belongs to M n cross n such that your last entry or first entry, whatever you want, you can take. A n n must be equals to A I equals to 1 to n minus 1. Right? If this condition satisfied, then trace will be 0. Right? So we have only controlled on this last entry. We don't have any control on the other entries, but we have control on only the last entry. Now, what is the dimension of this space? So dimension of all m cross n matrices is n square, right? But in this case, we have only control on the last entry. If you define these entries, then it will be depend on the other entries. The last entry, this entry will be depend on the other these entries. So you don't need to define this entry, right? So the dimension of this is n square minus 1. So n square minus 1, right? Okay, you can think it like this. So, okay, so what is range space? It is always a subspace of the codimension, codomain. What is codomain here?
R.
R. Okay, so this is subspace of R. What is the dimension of R?
1.
1. Right. Now, what can be the dimension of R of t? It will always be less than equals to dimension of R. So dimension of R is 1. So either it is 0 or it is 1. Right. So is it 0? Is it 0? You simply take this and 1 here. So what is the trace of this matrix? 0. But this always belongs to, okay, or range of t. Okay, we want range of t. Okay, so what is the value of this matrix? What is the value of this matrix? Suppose this matrix is B. So what is T of B? Other entries are 0. So what is the
1.
trace of this matrix? 1.
Yes, sir.
So 1 belongs to range of T. So dimension of range of T cannot be 0
0.
because 1 belongs to range of T. Dimension of G, if dimension of range space of T is 0, then the whole range space has to be 0 only, right? But here we have one non-zero entry, right? So it cannot be 0. So what is the remaining option? So it has to be 1,
1.
right? Okay. So what is the ring nullity theorem? So nullity of T is equals to dimension of V. What is the dimension of V? What is the dimension of V? N square.
And sir, yes.
What is the dimension of V? N square. So it is N square minus nullity of T. What is the nullity of T?
1.
1. So the dimensionality of rank of T. So rank of T is 1. So nullity of T equals to N square minus 1. Correct? So from using this linear transformation, you can find the dimension of this space also. This dimension of this space is N square minus 1. Suppose I replace this by M cross N matrices. Then what will be the dimension of, what is the nullity of, in that case, what will be the nullity of T?
N minus 1.
So again, in that case also rank is 1.
Yes.
Okay. And the dimension of V is, in this case, dimension will be m into n minus rank is
Yeah.
1. So in that case, nullity will be mn into minus 1. Okay. Okay. Now suppose I ask this question. Suppose you have a function r2 to r3, and you know what is the value of 1 comma 1, that is 1 0 2, and value of t 2 comma 3 is 1 minus 1 4, right? Can you tell me now, from these values only, can you tell me the value of t of x comma y? What will be the exact linear transformation? Can you tell me?
Yeah, it can be said because 1, 1 and 2, 3, these two vectors are linearly independent in R2 and the dimension of R2 is 2. So here we are given at the image of the basis element are given in R3, and whatever the vector in the R2 x in the form x comma y, it can be expressed in the unique linear combination of these given two basis vector, and that is why it would be easy to verify that form of the tfxy.
That is correct. So actually, you know the values at 1 comma 1, 1 comma 1 and 2 comma 3. So these are this, if you take this set 1 comma 1 and 2 comma 3, so it is actually a basis for R2, right? Now if you know the values at the points of a basis, then you can always find the whole linear transformation. Now, how will you find? So this is a basis for R2 because this is, both elements are linearly independent, that you can check. Now, since this is linearly independent, it will span whole R2. So that x comma y will be written as some linear combination, say alpha 1 comma 1 plus beta 2 comma 3, right? Now from this relation, you can find value of alpha and value of beta. Of course, it will come in terms of x and y. It will come in terms of x and y, and from that you can find t of x y equals to alpha times t of 1 comma 1 plus beta t of 2 comma 3, right? That you can find. Now this is your it is your exercise, that find value of alpha and beta. It will of course come in terms of x and y, right? Now the question is, next one is, can we find a linear transformation t from R3 to R2 such that t of 1 comma 0 comma 3 is equals to 1 comma 1, t of minus 2 0 minus 6 is equals to 2 comma 1? Can we find this linear transformation which satisfy these properties? So if you see carefully, so these two elements are not linearly independent, right? So suppose this member is your x, this is your y. So y is actually minus 2 times x, right? So since this is, if suppose there exists a linear transformation which satisfy this property, then what you can write, t of y equals to minus 2 t of x, right? So what is the value of t of y? This 2 comma 1 is equals to minus 2. What is the value of t of x? This 1 comma 1. Right. So this is minus 2 comma minus 2. 2 comma 1. So is it possible? So it is not.
No, sir. No.
Not possible. So there will not exist any linear transformation which satisfy this property, these values, right? The only difference is here these two members are linearly dependent, but here in this case these two members are linearly independent. So you can assign any value to linearly independent members. That will never create a problem. But if your members are linearly independent, then you have to take care of that. Okay. So as we did in this example, so what we can say the result, if you know t, suppose t is a linear transformation v to w and b is a basis for v, and if you know value of t on b, then you can find t, complete t on v, the whole space v also. You only need to find, if you have t, if you know t on b on a basis, then you can extend that linear transformation to whole v. Okay. Okay. I think we can solve some questions. Okay. So this is the question number 38 from 2023. So what this question says, so which of the following are true, right? So every linear transformation from R2 to R2 maps lines onto points or lines, right? So what this question says, suppose T is your linear transformation from R2 to R2, right? And if you take any line subset of R2, right? So without loss of generality, you can assume that this passes through 0. Otherwise, suppose L passes through any point, say x comma y. So suppose this point is capital X or capital, you can say capital P. So if you take this line L minus P, the new line L dash, so it will pass through origin. So T is linear transformation, so there is no difference between L minus P and L. So the same thing will happen, right? So you can assume that L passes through origin, right? So what is the dimension of L? It is line.
Equal to 2.
It is line. Okay, it is not only point. So it is a line. So dimension of line is 1, right? Now what can be the dimension of T of L? It will always be less than equals to dimension of, okay, you can write here also. So there is a result, dimension of T of W. So W is a finite dimensional subspace. Okay, I should write Y. So T is a linear transformation from V to W, right? Y is a subspace of V, right? So dimension of T of Y is always less than equals to dimension of Y. Infinite dimensional case. For infinite dimensional case, it may be infinite, it may be infinite. Both can be infinite. But for finite dimensional case, it will always less than equals to dimension of Y. Okay, it can be 0, it may happen that it is 0. So here the dimension of T of L will be less than equals to 1, right? So what are the possible cases? Either 0 or 1, right? So if dimension is 0, then it will maps to the 0 point only. So T of L will be 0 only. So it can, so points on 2 points also, it is true. So it can be maps to points only. Now the second case is if dimension of T of L is 1, then it will be it is a subset of, so it is a subspace of R2 and dimension is 1. So the only possibility is it will be a line, right? So lines will be maps to either on points or on lines, right? Right. So this is true, right? Now, so every surjective line linear transformation, second option is every linear transformation, surjective linear transformation, that is onto linear transformation from R2 to R2 maps lines onto lines. So what this theorem says, what this statement says, suppose you have a line L. So T of L, so is either 0 or it is a line from statement 1, right? Now T is surjective, right? So as we have seen earlier, so if T is surjective, then null space of T will be 0 only, because T is so dimension of domain and codomain space are equal, right? Dimension of domain and codomain space are equal. So as I said, T is onto if and only if T is bijective, if and only if T is 1 1, if and only if null space of T is 0, right? So null space of T is 0, right? So there is no non-zero point which maps to 0. Now in this line we will have non-zero points, so it cannot be equals to 0. So the only possible case is line only. So if T is surjective, then it will always maps lines onto lines. So this option is also correct, right? Now the next option is every bijective linear transformation. Okay, so every bijective linear transformation from R2 to R2 maps pair of parallel lines to pairs of parallel lines, right? So what are parallel lines? Suppose this is your line L1. So parallel lines will be like this. This is your parallel line L2, right? So L1 will always be equals to x plus L2 for some point x or some scalar alpha, right? So suppose this is your point, say x. So this point will be some x plus alpha, right? The same thing will happen for all the points. So you can always write x1 L1 is always equals to alpha plus alpha 2, right? Now if you apply linear transformation, so T of alpha 1 will be equals to, so suppose T is any T of alpha plus T of alpha 2, right? This is some, okay, this should be, so what should I write here? Okay, I should not write this one. Okay, so suppose T of alpha 1, right, and T of alpha 2. right? If you take any point in line this x in this line, so point will be of the form this, right? So it will be some constant alpha into, so it will be, so how to write this? So the point will be x plus alpha. I don't know how to write this. So if x is in this will be alpha
X
plus,
y goes to x plus alpha and y plus alpha.
yeah, correct. That will be, so your point will be of the form x plus x, this one, and this will be of the form x plus alpha and y plus beta, right? But it will be always be the same point, right? So if you calculate t of if you apply linear transformation, what you will get? So t of L1 is equals to t of alpha beta plus t of L2. So again you will get parallel line, right? So this one is also true. Every bijective linear transformation from R2 to R2 maps pairs of parallel line to pairs of parallel lines. Even it is a standard statement that every linear transformation that is 1 1 from R2 to R2, even it is bijective or 1 1 or surjective. Any linear map from R2 to R2 which is either 1 1 or surjective or bijective, that always maps parallel line to parallel lines. Okay, now the remaining one is D. So every bijective linear transformation from R2 to R2 maps pair of perpendicular lines to perpendicular lines. So what can you say about this statement? You just take this linear transformation R2 to R2. Okay, so x-axis and y-axis are perpendicular, right, to each other. Now y-axis is just a span of 0 comma 1, right, and x-axis is just span of 1 comma 0, right? Now you define linear transformation as this member maps to 1 comma 1 and this maps to 1 comma 0, right? So what is the span of 1 comma 1? This line y equals to x, right? And what is the span of this 1 comma 0 is again x-axis. So what I'm saying, you define linear transformation as x comma 0 is x comma y equals to, so x comma x plus y. If you define linear transformation like this, then your x t of x-axis, it should be x comma x. So then x-axis or x plus y, or it should not be like this. So your this will be, so x-axis should be mapped to x-axis only. So the x comma plus, then this should map to the y is equals to x. So what should be your y here? Okay, 1 second. So this is x1 1 plus y 1 comma 1. So it will be x plus y comma y. Yeah, correct. So define your linear transformation as x plus y comma y. Now, what is t of 1 comma 0? This is 1 comma 0.
1 comma
And
0.
right. So what is the image of x-axis? Span of this is equals to span of this, image of this. So this will be x-axis only. Right. Now what is the image of y-axis? This is span of 0 comma 1. Now what is the image of 0 comma 1?
1 comma 1. Sorry. The
1
y-axis.
comma 1. And the span of this. This is x equals to y line.
Yes.
And both these lines are not perpendicular. Okay, you just take this linear transformation and you can see that this is bijective, linear, but it does not map perpendicular lines to perpendicular lines, but it will always maps parallel line to parallel lines. Okay, so this is not correct. Okay, the next question is from 2023 39 question number. So which of the following are linear transformations? So first one is t of x equals to sin x. So is it linear? Is it linear?
No.
No. Why?
Because sine of x plus y is not equal to or necessary equal to sine x plus sine y.
Okay, what is sine pi by 2 plus pi by 2? What is sine pi by 2 plus pi by 2?
Pi.
This is sine pi. What is sine pi?
0.
0. Now what is sine pi by 2 plus sine pi by 2?
1, 2.
This is 1, this is 1. So 2. So both are not equal. Right. So it
Yes.
is not linear. So this is not linear. Correct?
Mm.
Yes.
Okay. We have just seen this is a linear transformation.
Mm.
Right?
Yes.
Now, what about the third one? So this is a linear transformation. What about the third one? So is it a linear transformation? Sorry.
So this is not linear transformation.
Yeah, this is not. Why?
So because zero element does not map to the zero element.
Yeah. The zero element member of R2 is 0, comma 0. Now what is the zero member of R is 0. Now what is the image of t comma 0 0? So 0 plus 0 plus 1. This is not equals to 0. Right? So 0 maps doesn't map to 0. So this is not linear transformation. What about the third one? The last one. D option. So t of p of x is equals to p of 1.
Linear.
This is linear. You just what is p x plus q x? If you apply t here, it will be p of 1 plus q of 1. Right? So this will be t of px plus t of q of x. Right? Similarly, you can check alpha px is equals to alpha times p of 1. It is equals to alpha times t of p of x. So it is linear. Right? So B and D are linear transformations, but A and C are not linear transformations. Okay. Now the other one is, suppose T is a linear transformation from P to R. So P to R is what is the basis for P to R? 1 x square, right? So with the linear transformation given by p of x equals t of p of x equals to p of x square, right? Find the rank of t. Now what is the image of t of 1? 1, right?
Yes, sir.
Now what is t of x square?
Yeah.
Now what is t of x square? X to the power 4. Now all these three are linearly independent and also belongs to range of t, right?
Then
So what is the rank? It should be greater than equals to
3.
3, right? Now, but what is rank nullity theorem says? Rank of t plus nullity of t, this sum should be equals to dimension of the domain space. What is the dimension of domain space?
3.
What is the dimension of P2R? 3,
3.
right? So rank nullity theorem is saying the sum should be less than equals to, the sum should be equals to 3. Now this, the previous thing says rank is greater than equals to 3, right? Dimension cannot be negative, so this rank should be 3 only, and nullity should be
0.
0 only. This is the only possible case. Okay, now this is question number 40 from 2022. Suppose t is a function from M3R to M3R, right? Now which one of the following is a linear transformation? P is a fixed matrix. P is a fixed matrix. Now which one of the following are linear transformation? It should be R, right? Now if you see the first one, now what is T of A plus B? It will be A plus B into P minus P into A plus B. So it is equals to AP
Understand.
plus BP, right? Minus PA minus PB, right? So it is equals to AP minus PA plus BP minus PB, right? So this is image of T of A plus this is image of T of B, right? Similarly, you can check T of alpha A is equals to alpha TA. So it is linear. Now what about this one? So it is not linear. Why? So A square. So if you calculate T of A comma B, A plus B, so it will be A plus B square P minus P square A plus B. So here we don't have any problem. So but in the first term, what is it? This term is not equals to A square P plus B square P. In general, it is not equal. These two terms are not equal, so this is not linear. Even you can find examples also. Similarly, if you do the same thing is happening here also. Here you have A square. So if you calculate A plus B, you will get A plus B P square minus P A plus B to the whole square. So it is not equals to PA square plus PB square. So this is also not linear. Even you can take precise matrices also, you will find that both these terms are not equal. Okay. Now in this we don't have any square or any power on A. So if you calculate a plus b, t of a plus b, so it will be a plus b p square minus plus p square a plus b. So it is equals to a p square plus b p square plus p square a plus p square b, and this is actually equals to t of a plus t of b, because first you take this term and this term, then you take these two terms. So this is t of a plus t of b. Right.
Will be
Similarly,
linear.
right? Sorry.
So it will be linear.
Yeah, it will be a linear transformation alpha t of a. Okay. So let me write one question here. Suppose T is a linear transformation. Okay, you can easily tell me this question. Suppose T is a linear transformation from V to R. V is a, both are on the field R. Okay. Now I'm saying T is non-zero also. Okay. So what is the codimension of null space of T? You think about it. It is actually easy. Okay. So with this, let me stop here. Later we will see maybe eigenvalues, eigenvectors, or matrix representations of a linear transformation. So if you have any questions, you can ask.
Sir, please could repeat this last one question, which is left for our thinking.
Okay, suppose T is a linear transformation from V to R, and the field is R. Okay, is a real linear transformation, and I'm saying this is non-zero. And the question is, what is the codimension of null space of T in V?
Okay, sir. And the first one, the convergent sequence and the sequence which are convergent to 0 point and related to codimension, whatever you have done for us in the very beginning, there are some problem about
So I
some
did
confusion.
this from that question only. You have any doubt in that question?
Yeah.
Okay, so where I did that? Okay, this one.
Yeah.
So C naught is the sequence of all.
Yes, here
Is my screen visible to? Okay, yeah,
screen, yes, visible.
yeah.
And
So what is your
yeah,
question?
there C0 is a subspace. It is clear, and I I am as I am asking that you have written the procedure in constructing the Z, and from that point, from here I am doubting. The We are taking x in belongs to C, which is converges to x,
Hmm.
and x is fixed. Fixed means uh, there are so many x, okay,
No,
and
no,
fixed.
no. There are not. There is only one X where the sequence is convergent.
But
Limit is
particular
always
one
zero.
sequence.
Yeah, for
Here,
particular sequence, I have fixed the sequence in the very first step. I have
mm,
fixed the sequence.
yeah, and this x is the fixed point for the whole set of sequence which are
No,
convergent
no,
to
no,
x.
no, 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 no. It is not fixed for every sequence. Suppose you give me any yn sequence which converts to y, then I will write this. So my claim is you can write. So let me add one page here. Okay, so my claim is you can always write C as C naught direct sum span of this Zn sequence. And what is your Zn? Each entry is 1, the one sequence,
Mm.
right? Now you give me any sequence yn. Suppose yn is a sequence in C, right? So
Yeah.
yn will converge to some point y,
Yes.
right? Now in the previous case, what was my case? So xn, you can write xn sequence as this xn minus x sequence,
Yes.
right? Plus
Yes.
x into zn. So this is a member of C
C0.
naught, right?
Mm.
So this is a number only. Now in this case, now in yn case, it will be yn minus y plus y into zn. Whenever
Yes.
you change your sequence, this constant will change.
Yes, sir. Say once again this line.
When you change your this sequence,
Yes, sir.
so this y will change, this y will
Yes.
also change.
Yes, sir.
But this will be your fixed term
Yes.
zn. That's why we
Yes.
are taking span of zn here.
Yes. Yes. Okay. Okay. Okay, sir. And this is that one element, non-zero element. Therefore, that is why it is a dimension of one.
Yeah, this is
Yeah.
dimension of this
Mm.
is dimension of this space is, suppose you could denote this space as by y, then dimension of y is 1, because this is a
Mm.
non-zero element, and it is span of y is span of this member.
Mm.
So dimension is 1, right?
Yes.
And you can write any member xn as xn is a member of C, so you can write it as xn minus x. So xn converts to x, then xn minus x will converge to 0, so it will belongs to C naught plus this is Zn sequence. Now I can add any scalar here, so
Mm.
I'm adding here x.
Okay. 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 It's now clear. And this is a something new question to me. I have not encountered some types of construction and sequence related question in this dimension and linear algebra portion. Sir,
Even this is a very interesting question, so
yes, yes,
I thought
yes,
you
and
know
sir,
this.
to acquainted in this new type of concept and how can we get some types of question? Can you provide in the
You have to think about that. Like suppose you have now suppose I make it a C naught naught, the
yes,
collection of all eventually zero sequences.
eventually zero sequence means yeah.
Means after a step xn belongs
Or
to
okay,
C
okay.
naught naught, then xn is, have you heard about this term xn equals to 0 for all but finitely many n?
Uh, yes, yes, yes. That is eventually zero. Okay.
That is eventually zero sequences. Means
Mm.
after a few steps, your value will be 0,
Yeah.
right? Now the question is, what is the dimension of this? Now, what is the basic dimension? Of course, it is infinite. Now the question is, what is the basis of this?
Yeah.
Whatever you example uh, can think in the real analysis, you should ask
Mm.
these questions. Dimension is of course infinite, but can you find basis for this?
Yes. Mm.
Okay, you think about it. C naught naught is a subset of C naught,
Yes, yes.
right? This is subset of C,
Yeah.
right? Now suppose I'm writing here W as all the sequence xn such that this xn is convergent. This summation is convergent. If even what is absolutely convergent. Is convergent. Absolutely convergent sequences. Now the question is where this W will lies between these spaces, because this is also a sequence. Now this you can ask to yourself. Like, you can put many questions like this, where this W lies. So of course, if you take C, you can verify that C naught naught will always be a subset of W. And if you remember, if a sequence is the series is convergent, then this mode action will always converge to 0,
Mm.
right? If this is 0, then this will imply action is also converged to 0. You, you remember this? If mode action is converged to 0, then action will also converge
Yes,
to
yes,
0,
yes, yes, yes.
right? So this is a subset of C naught.
Mm.
Now the question is, now suppose I'm not asking about this. You just take action square is convergent. Sequence action such that this is convergent, right? And the question
Yes,
is, suppose this is your W, and this space is actually called L1 space, small L1 space. So C naught naught is subset of L1. This is subset of C naught. This is subset of C, right?
yes,
Now,
yes,
where this new subspace, suppose W2, where this space will lie, like
yes.
this, like how the examples you are encountering in real analysis or in other areas, you should ask whether it is form a vector space. If it is forms a vector space, what should be the dimension? If it is infinite dimensional, so what should be the basis? If you are not able to find the basis, so can you relate those examples with the existing examples? Like these, you can ask to yourself. What is
Okay,
the
sir.
relation between other examples like this? You can ask to yourself.
Okay, sir.
Okay. Any other question?
No.
Okay, so can we wind up, sir?
Yeah, sure.
Ah. Okay, the next session will be on Monday, that is on 29. Yeah. Okay, thank you, sir. Thank you, sir.
Okay, thank you.